let's have a go at question 4 from the 2017 VCAA exam. Been asked about this one a few times as well. So what we start with is this exponential function, and we go straight into a transformation problem. So the transformation that maps 2 to the x onto this function here, so 2 to the x onto this function here, you can see by recognition it's going to be 1 to the left and 2 units down. So c will be -1 and d will be -2. C equals -1, d equals -2. If you're not confident on that, you probably want to run the mapping. So we've got y equals 2 to the x, and y equals 2 to the x plus 1. Take 2. Y equals y dash plus 2. X equals x dash plus 1. You can see why recognition's helpful. It just takes time. And x dash equals x take 1. Oops. Right, so yeah, 1 to the left, 2 units down. Find the rule and domain for f-1, the inverse function. So we started with y equals 2 to the x plus 1. Was it 2 to the x plus 1? Take 2. So the domain, because it's exponential and it's unrestricted to all reals, the range of the function is from the asymptote not including up to infinity. So let's invert it by swapping x and y. So I've got x plus 2 equals 2 to the y plus 1. So my inverse function is f-1 such that -2 to positive infinity, because the domain of the inverse is the range of the original, to codomain all reals. Now what we're going to do is we'll just drop this into log form. So we got log 2 x plus 2 take 1. Cutting corners. f-1 x equals log 2 x plus 2 take 1. Right, find the area bounded by the graphs of f and f-1. So I can sort of see what's going to happen here is we've got this log. We go like that. Right, and what it will do is intersect with the original function. So this will be f-1, this will be f of x, and what we'll do is we'll basically run along the line y equals x, which is where a function will intersect with its inverse. So we'll solve f of x equals x for x, and what that will do is give us the terminals that we use for our integral problems. So define f of x equals 2 to the x plus 1, what was it? X plus 1 take 2. Solve f of x equals x. Okay, so x equals -1 and x equals 0. Area equals integral 0, -1. Now, top function is going to be x, bottom function is f of x. And what we'll do is then double that result. Okay, so that'll the below part, and then we'll double it to get the above part as well. Okay, so slam that into the calculator. 0, -1, x take f of x dx multiplied by 2 gives us that, and when we simp it, it gives us that. Okay, so good, or so far so good, should I say. What next? Part of the graphs of f and f negative 1 are shown below. Find the gradient of f and the gradient of the inverse at x equals 0. Okay, so the gradient at x equals 0 is going to be the gradient of the tangent at that point and the gradient of the tangent at that point. Right, so let's get the gradient of the original function by diffing the function and subbing x equals 0 into the derivative. And is going to be 1 over that. Basically, like if you sort of, let's just go to linear and think about this line here. If this line here is y equals 2x, then if you invert it, right, this line here will have a gradient of 1 on 2x. If you're not too sure though, what we'll do is we'll just go ahead and define the inverse function. What are we doing? Log 2 x plus 1 take 1. That's wrong. That should be x plus 2. Okay, now diff g of x with x equals 0. Yeah, okay, that's that there. Okay, the functions gk, where k is an element of all real positive, are defined with the domain R. Okay, find the value of k such that gk of x is equal to f of x. So remember, f of x is equal to, what was it? 2x plus 1 take 2. I can't really do this by recognition. So yeah, let's just go ahead and define g of x equals 2 times shift e k times x take 2 and solve g of x equals f of x for k log e2. So that's, I think, basically saying that if I jam that into that, it'll look like f of x. Let's just see if that happens. F of, let's do g of, I think it'll still keep it in log e, but let's see. 2 to the k plus 1 or x plus 1. Yeah, there you go. All right. So let's go with the next one. So find the rule of the for the inverse function. Yep. Okay. So we'll go. What's this? So y. So find the rule. Rule only. Don't want the domain. 1 mark. Y equals 2 to the e k x take 2. Swap x and y. X equals 2 e to the ky take 2. Log e, I don't know why I tried to do this all at once, x plus 2 onto equals ky, gk negative 1 x equals 1 over k log e x plus 2 onto. Describe the transformation that maps g1 onto the graph of gk. So here's gk, and g1 is going to be 2e to the x take 2. So we just, where we see k, we put 1. So what are we going from? That to that. So this to this, which is going to be a dilation factor 1 on k from the y-axis. All right, and so yeah, to do that, what I would do is pop 2k into that, which would be a dilation 1 on k. Yeah, cool. All right, describe the transformation that maps g1. Okay, so that's working with the inverse. So here's the inverse, and we're talking at g1. So we're going from this to this, which is obviously dilation 1 on k from x-axis. Okay, the lines L1 and L2 are tangents at the origin to the graphs of GK and GK negative 1 respectively. Find the value of K for which the angle between L1 and L2 is 30. Well, it's going to be a similar scenario to these, and what we'll be after is an angle here between them. I know that this is F and F negative 1, but all GK negative 1 and GKR are just transformed versions of this by a factor of k and 1 on k respectively, I think. So yeah, essentially what we want to do is the angle between the function's tangent and the tangent to the inverse at 0, we want the angle between them to be 30. Now what we can do basically is we can so this is the top function here. So let's just sketch this up to work out how we're going to do this. So we've got the exponential, we've got the log, right, and the tangents between them. So what we can do, this top tangent here, if that one is going to be 60 degrees, then the tangent to the bottom one is going to be 30 degrees. That'll be 30 degrees from the top, which will be 30 degrees in between. So essentially what we want to do is I'm going to, so what's g of x again? G of x is the original function. So what I'm going to do is I'm going to find gk dash x equals, which is that, 2k e to the kx, gk dash 0. So let's put 0 into the derivative to find the gradient of the tangent at that point. X equals 0. It's 2k. All right, now what I want is that is the gradient at x is equal to 0. And what I want is I want it to be 60 degrees. I want this to equal, so 2k needs to be 60 degrees. Okay, and 60 degrees m equals tan of 60. So I'm just using m equals tan theta here. M equals, what's the tan of 60? Root 3. Root 3, k equals root 3 on 2. All right, so yeah, we could have done that with this one, or we could have done it with the inverse function. It would have worked out to be, or it would work out to be the same answer. All right, so let me explain this one here. So to do it properly, I'll just use GeoGebra to do it. Right, so what we'll do is we'll graph the original function. Where is it? Okay, so g of x equals 2 to the power of, no, not 2 to the power of, 2 multiplied by e to the power of k times x take 2. All right, then we'll invert it. Okay. There it is. Right, so right, let's put a point at 0, 0. Let's grab a couple of tangent lines. So tangent here to this, tangent to this one. All right, so what we're basically doing here, we want the angle between these to be 30 degrees. So what I want to do basically is make this top one, I want this one here 60 degrees, or I want this one to be 30 degrees. 60 then take away 30 is going to leave 30 in the middle. Right, so that's essentially what I'm doing now. Root 3 on 2 is approximately 0.866. So if I rock that back, so that is 30 degrees. That would be roughly 30, well not is, but roughly 30 degrees at the moment, right? And then it just gets bigger or smaller depending on what it is. All right. Right, let P be the value of K for which GKX equals GK negative 1X has only one solution. So that will be the scenario where, like, it's basically going to dilate far enough that, like, they go like this, all right, that they'll touch just there. Otherwise, they're going to do that thing of, like, overlapping. That's a bad sketch, but they're going to do that thing, like, can't really see it there, but yeah, so what we want is this scenario here. So we want the value of P where this occurs. Now, what we want is the gradient of this tangent to equal the gradient of this tangent. Right, so we worked out the gradient of the first tangent, so we know that m of gk equals 2k at x equals 0. And the inverse function, that one is going to have m gk negative 1. It's going to have a gradient of 1 on 2k. because of the same reason that we got this scenario happening here. So it'll be 1 over. Now what we'll do then is we'll go, they need to be the same, 1 over 2k. So that's going to be solve 2k equals 1 over 2k for k plus or minus a half. K equals plus or minus a half. What's k? K is an element of all real positives, but k is an element from 0 to positive infinity. Therefore, k equals a half. And let p be the value of k. So k equals a half, therefore p equals a half. All right, let's just see what happens when I do that. Well, it's happened. That's the way I left GeoGebra. So when k equals 0.5, what happens is we get that single intersection point for every other value of k. We're going to get this double intersection. I wonder what negative a half does. All right, okay, so that's the case. Oh, you get some reflection. I don't know how that works or why that works. Anyway, obviously, yeah, they don't want that, so they rule that one out. It's only the positive version of it that they want to keep. All right. Okay, let A of k be the area bounded by the graphs there for all k greater than p. State the smallest value of b such that A of k is less than b. All right, so the smallest value of b such that the area is less than a particular value. So k is greater than p, for k greater than p. Right, so basically we're going to increase k far enough. Well, k is going to tend to positive infinity. Say the smallest value of b. All right, let's see what happens. So what we'll do is, let's go to, okay, I'm going to go g of x to get that. I'm going to copy that and go over to graph and table, get rid of this, set that back to default, and graph it via a parameter. And what happens if I, yeah, all right, yeah, anyone from my school watching this, this is basically what that question was about the football field on that sack. So yeah, so what's going to happen, this is probably where I got the idea for that question actually. So as it tends, or k gets larger and larger and larger from p, so larger than a half, what you can basically see, I'll just draw the y equals x function on there. You can see basically that it forms a square area 2 by 2. I can do the inverse as well. Analysis, sketch, inverse to this thing. All right. Oh, won't do it. Anyway, what's going to happen is it will just it'll become like a square, so a 2 by 2 square. So state the smallest value of b such that A of k is less than b when k is larger than p. So the smallest value, what's the smallest amount that A of k can be less than. So basically the cutoff point. So B is equal to 4 in this case. Now we'll go less than 4, okay, but we want the smallest value B can be, right? Because yeah, as we approach k equals that value there, it's going to get, the area is going to get smaller, but this, we want to complete this statement. So we want to say that the area is less than a particular value, and we want the smallest value of B such that this can be true. Okay, so B, as it approaches infinity, B has got to be less than 4. We'll see a smoother animation of that probably. No, let's let it approach. So there's K5. Let's send it up to 100. So you can see here, basically as it approaches 100, or even larger, you're just going to get a square. Okay, and we want the smallest value of B. All right, so there it is there. All right, a couple of really tricky problems to finish up with.